we should be seeing our electron flow up out of here and then into over here. Okay, if we're going to start to do that, what happens on the anode side? What's going to happen to the charge over here? If electrons start leaving, what charge appears? It's going to start to become more positive. And if electrons start going into the cathode side, it starts becoming more negative. This is going to set up problems for us. Okay? The primary reason we've got problems is that charge is ultimately unstable and bad, and we want to neutralize that charge. Did you all get it? Don't stress. And so if we're building this charge in those individual wells, we're actually not going to get electric flow. Okay? Our electrons might flow for a little bit, but it's going to shut down pretty quickly. Okay? If we think back to an electrical circuit, I can't just attach a battery with a little wire to my light and then hope the light works, right? What has to happen? I have to complete the circuit. I have to have another way for the electricity to run back down or run back through. The same thing is going to hold true with our voltaic cell. For us to actually allow for the electrons to flow, we have to complete the circuit and neutralize that charge as it's going through and forming. Okay, so as this is drawn, we've got a problem because we haven't completed the circuit. To go through and complete the circuit, I would need to somehow connect these two sides. Right? And I want to connect them in a way that would allow for the passage of ions back and forth. And the main reason I want ions is that if I'm starting to lose electrons, I shouldn't have erased everything over here, this side starts to become positive. What's going to happen in that channel in between is that ions are going to flow towards that positive. What charge will those ions be? They should be negatively charged, because what they're trying to do is cancel out that forming positive charge. Right? What's happening at the cathode, where it's gaining electrons? That was starting to become negative, so what's going to happen to it? What's going to flow towards it through the channel? Our positive ions. Right? And it's that now continuous loop that's going to allow for our electrons to flow. And that process, or that section in between, is what's known as our salt bridge. The salt bridge will allow for those ions to pass back and forth, and that's what's going to allow for the neutralization of the electron current, okay, through the wires up above. Kind of make sense? So the net result is that there isn't a change in charge, okay, but our electrons are still allowing to navigate. Kind of, sort of? Okay. We're going to reference this kind of diagram again in a little bit. So how much energy is released by the voltaic cell? This comes back to our cell potentials. Okay, so what we've gone through and done is looked at individual reactions. We defined the state at which we're looking at them. So standard conditions is 25 degrees Celsius, 1 atmosphere pressure, and all your reactants and products will be 1 molar. Okay? When those conditions are met, we'll then record the amount of volts produced. Okay? Volts are similar to kilojoules, they're just a different unit system because discovered by different people. Okay? So if we're looking at kilojoules, the kilojoules is our bond energies. If we're looking at voltaic cells, what we're looking at is electric flow. Because we're monitoring those things in slightly different systems, we get slightly different units associated with them, which is likely due to just historic reasons of how they were discovered and ultimately measured. Okay? But ultimately, they're going to refer to the exact same thing. There's an energy differential in those systems. And if there's an energy differential in those systems, shouldn't you be able to relate said energies to each other? Yeah, you should. Okay? And that's where we would encounter, delta G being related to our cell potentials. Okay? Before we go into that, let's go through and take a look at some half reactions. So when we study these individual reactions, We could define that cell potential or standard potentials in any system we wanted. They could be reduction potentials, they could be oxidation potentials. For whatever reason, and I don't know the history on it, we've decided to summarize and report them always as reduction half reactions or reduction potentials. So when we're looking for our cell potentials or our potentials for each of those reactions, you have to realize they're always going to be provided according to the reduction half reaction. Why does it become important? Well, if I want to know the standard cell potential for a voltaic cell where zinc is oxidized and copper is reduced, I'm now going to have to take that language and apply that language to the chemical reactions above to organize them into the proper orientation of chemical reactions so that I can then calculate my cell potential. It is officially a blue box. You guys want to give that a shot? 3, 2, 1, yes, go. So in working through this question, we're seeing a variety of people going through and just adding numbers and subtracting numbers. Adding and subtracting numbers don't work if they aren't in a proper context. So you have to know the context that runs with them. So if we go through and look at the question given, it says zinc is oxidized. What does it mean for zinc to be oxidized? That has to be a loss of electrons. If we go back and look at zinc, is it being oxidized in the equation given? No. So what we would have to do is flip that equation. I'm just going to put it there. So that we could go through and see that zinc is being oxidized. What's going to happen to the cell potential? Or we'll just call it cell potential because I don't know a better word to call it. What's going to happen to our cell potential? Well, the cell potential we've got is negative 0.762. When what? When it's reduced. Is it being reduced? No, so what do you have to do? You have to flip the sign. You're going to have to make it positive. Okay. What happens when copper is reduced? That would be the gain of electrons. Gain of electrons, is that what's being shown? Yeah, so I could immediately copy that equation down. 2 electrons plus our copper plus 2 goes to our copper. Okay, the cell potential for that reaction as written was 0.342. Did I do any flipping? No, since I did no flipping, there's no need to change the sign, so it is what it is. If I run my reaction, the electrons balance out. I can now look at the overall reaction of copper plus 2 plus our zinc. Goes to our zinc plus 2 plus the copper. What's my cell potential going to be? Just add those two numbers up. Okay, said 1.4, 1.1.
0.4.
Okay. And that now is our standard cell potential. So what we have to do is be careful with how we manipulate it. You'll note that within this format, I'm not using a particular formula to go through and solve this. Okay, what I have seen people try to go through and do, and I'm going to butcher it because I don't know it, is that our cell potential is equal to the reduction potential for whatever was oxidized. Actually, it's going to be whatever was reduced minus the reduction potential for whatever was oxidized. Okay, which formula is fine, absolutely. But now you have to memorize this formula. In particular, you have to memorize why you're using a minus sign. What that formula has done is removed the content. What content? The content we literally just walked through to solve this. So if you understand the content, you don't need a formula. Okay? That's the beauty of understanding. Okay? The formulas come from an understanding. Push the understanding and you don't need to deal with any kind of formula system. Okay? That will also mitigate the issues of, well, did I subtract the right one? Okay? Because it's ultimately a 50-50. Right? If you're like, well, those odds aren't bad, do you want a 50% on your quiz? And if your answer is yes, you should reevaluate your priorities, okay? Because that's not a passing grade. Okay? And if your answer is no, then stop doing the actions that put you in a 50-50 position. Shift to actually looking at the understanding of the content. Does that make sense? Okay. So we have the cell potential. This is correlated to some kind of energy, and that's where we could bring in delta G. Okay, for the reaction we looked at, we got a cell potential of what? Well, let's see if I can hold it in my head this time. It was 1.104. Hey, look at that. Okay. That correlated to a positive cell potential, and that meant a spontaneous chemical reaction. But if we think back to delta G's, is a positive delta G spontaneous? No. A positive delta G is not spontaneous. Okay? Which sets us up with a problem. In one unit system or energy system, positive is good, and in one energy system, negative is good. We've got that change in sign. We've got yet another 50-50 that we have to be careful with. Okay? So this is where we can go back to our chemical formula, and we notice that we have the minus sign being dropped in. The whole point of that minus sign is so that we can align those two unit systems, those two energy systems. Kind of make sense? The next part that we have to worry about is that we've got this N and this F floating around. The F is ultimately a conversion factor. Okay? It's Faraday's constant. We use that because if I take coulombs times volts, what do I get? I get joules. Okay? So really, this equation is just how do we convert from one unit system to another unit system? That's it. That's the whole point. That's what we're doing within it. Okay? Why do we want to do that? Introduces a whole other layer of questions that you won't be happy with, but we'll deal with those in a little bit. Okay? What's the N? Because what we're talking about is the number, there's our N, it's the number of moles of electrons that are transferred through this chemical reaction. Okay? To determine the number of moles, we would have to go back to our half reactions and ensure that we've properly balanced them out. So for the previous reaction that we ran, the electrons, how many electrons were transferred? 2. So our N is 2. We could then go through, plug in our numbers, and we could determine what our delta G would be. Kind of, sort of? Okay. So, why not? Calculate the delta G for the voltaic cell where zinc is oxidized and copper is reduced. Is this reaction spontaneous? Right? If you'd been paying attention, or even if you hadn't been paying attention, hopefully you noted your formula for calculating delta G. So now it's just a question of plugging things in and going through and solving. So if we're going to set it up, delta G equals N. We'll come back to that in a second. What was F? 96,485. What are the units on F? I technically already forgot them. Coulombs per mole of electron. And then our cell potential, which is 1.104 volts. The tricky part here is going to be what is our N. If we go to the overall chemical equation, do you see the number of electrons? Do you see any electron? You see electrons? What's the symbol for electron? E. Where do you see an E? Okay. Okay, and that becomes one of the challenges on determining that N, because it's not usually explicitly stated in your overall reaction. In fact, it should never be in your overall reaction. Why not? Why do we need to have them cancel out? Why should they never appear in an overall equation? Electrons are inherently unstable. Okay? They can't just exist freely on their own. As soon as we're in a solution, those electrons are going to very quickly react with something to neutralize that electronic charge very, very swiftly. Right? That's why when we look at a chemical overall reaction, we will never see an electron chilling in our equation. If we do, that means we did something wrong. Right? So to figure it out, what we could go through and do is split our reaction into the half reactions, where we just look at the species that are changing. To go from zinc to zinc plus 2, what had to happen? It had to lose, which means I'm looking at the product side, 2 electrons. How do I know it had to lose 2 electrons?
Because it was neutral first.
What we're doing is starting with our charges. The reactant side was 0, the product side was a plus 2. To make those 2 charges equal each other in an overall reaction, I have to account for the electrons in some fashion. Since the electrons are negatively charged, if I add 2 negative things to the product side, I'm effectively subtracting 2. Plus 2 and negative 2, that gets me my 0. This provides a nice internal check, because if you're like, I don't really know where it belongs, take a guess. So let's be wrong. I'm going to guess there was a reactant. What would my charge now be on my reactant side? Each electron's a -1. There's 2 of them, so the charge from the electrons is -2. How much does the zinc contribute? 0. This has to equal the charge on the other side. What's the charge on the other side? A +2. Did I get closer or further from having my charge balance? Further, which means I put the electrons on the wrong side. So what should I do? Put them on the other side and now push through. Okay? So you can leverage kind of a guess and check approach. All you're trying to do is neutralize that charge. Kind of make sense? All right, so in this case, what we're doing is transferring 2 moles of electrons. It's now just a question of punching it into the calculator to get an answer. All right, someone do it? You don't even want to tell me? Okay, I get it. This is in units of joules, so if we convert it to kilojoules, we can drop it down to -213 kilojoules. It's negative. Is that spontaneous? The cell potential had to be positive. Why is it spontaneous? Cell potential had to be positive. It's an easier statement to fix. What did we just solve for? We solved for delta G. Who gives a flying rat what the cell potential is supposed to be? I solved for delta G. Delta G is negative. And because the delta G is negative, it's a spontaneous equation. Kind of, sort of? So you're going to need to make sure you keep track of what you've solved for. Okay? If you get a number at the end that's negative, did you solve for delta G or did you solve for cell potential, E? Make sure you know what you've solved for. The same thing goes back to looking at our equilibriums. When we put in X into our expressions, what the hell did X mean? Make sure you know what you're solving for so that you can answer the question that's asked. Yes?
Are we ever, for these like voltage source kind of reactions, are we ever going to have a positive delta G? Because it doesn't look like...
So what would a positive delta G mean if we looked at a cell potential? What would our cell potential be if we had a positive delta G? It would be a negative voltage. What does the negative voltage mean? I don't get electrons flowing, ultimately. Okay, well, if the electrons don't flow, is that useful as a battery? No. Are there other things that have electrons flow or not flow that we might want to pay attention to other than batteries? Yes. And so what that's going to do is now change our interpretation. So could we encounter a situation where we run a calculation and get a positive delta G? Yes. What does that mean?
Voltage.
Negative voltage. What does that mean?
It's not a battery.
We could say not a battery. That works. One stage less. Not spontaneous. That's all it means. Okay? That's what that's going to come down to. It's a non-spontaneous reaction. Okay? So for spontaneous reactions, delta G is negative, cell potential is positive. Non-spontaneous, it flips. Okay? A voltaic cell must contain a spontaneous reaction to release energy. Okay? So in the system where we're getting a negative, we're not going to be able to release energy. What would we have to do? If we wanted that reaction to happen, what's going to happen is we're going to have to put energy into it to force the reaction to happen. Okay? That input of energy is now doing a different thing. We're not now trying to collect energy. We're trying to force that chemical reaction to happen. And by forcing it to happen, usually what we're looking at is something like electroplating. Okay? We're supplying the energy to force the chemical reaction to happen in a way that wouldn't naturally occur. So you're leveraging a different system to get a different end result. Okay? So for a reaction to occur, we need to have this positive cell potential. So in this case, what we could do is look at a list of half reactions. Note all the half reactions are listed as reductions. That has been our accepted default presentation for our potentials. Okay, so if I want to make a battery using lead and aluminum, which species is oxidized and which would be reduced? So to answer this question, what do I have to do? I have to find lead and aluminum and my reduction potentials. Okay, and before we get too excited and go, oh, there's lead way up there at the top, I would argue we're not looking at lead there. We're looking at different lead ions. Okay, so that's probably not the cell potential we're being asked to evaluate. What we're actually being asked to evaluate, come on, pen, would be the lead reduction potential there. And then where did aluminum go? There it is. And our aluminum potential here. Okay, so to go through and answer this question, which one's going to be oxidized? Which one's going to be reduced? Blue box. Talk at your tables to process what you think you need to do. I want to talk through this a little bit. So what I noticed was I don't think I saw anybody write anything down. Okay, which is great because you're able to think through this potentially in your head, assuming you actually get the answer right. Okay? That's fantastic. But what if you are one of those students that doesn't understand how someone went through and did this? Okay? Well, now you can't get the answer right. Okay? To figure out the answer, what you should be trying to do is not think in your head. Thinking in your head can actually lead to lots of errors, okay, for the general populace. Okay? There's always exceptions to that. And everybody goes, well, I'm the exception. No, you're not. Like, you just aren't. Okay? The vast majority of people cannot hold all of these things in their head, and so we need to write them down. Okay? This is, again, a 50-50. One thing's being oxidized, one thing's being reduced. So what should you do? When in doubt, yes. Okay? So what does oxidized mean? Loss of electrons. What did reduced mean? Gain of electrons. So you know what? I see oxidized first, so I'm going to say that lead was oxidized. So I'm going to take a look at my half reaction. For lead to be oxidized, it has to produce lead ion plus 2 electrons. That loss of electrons, remember equilibrium, right? 2 electrons would have to be on the product side. What would my cell potential be? Well, the cell potential for the reduction was negative 0.13, but what did I do? I flipped the equation, and since I flipped the equation, what do I have to do?
Signs.
Multiply by a negative. Okay, a negative times a negative would be a positive. Okay, I only have to flip one, which then means I could just go through and write out the other equation. We've got our 3 electrons plus our aluminum plus 3 goes to aluminum, and I get a cell potential of negative 1.66. Right? We'll encounter a couple issues here that we're going to gloss over, and we'll come back to in a second. But we could go through PB plus 2, more or less, a little bit more on the less side. And my cell potential is going to be, I just add up those two values now. So a 1.66, negative 1.66 plus 0.13 means I get a negative 1.53. Really? Oh, yeah. Yeah? No, you're right. That makes sense. Like I said, I use calculators. I don't do stuff in my head well. Okay? Is that a spontaneous reaction? Okay? I want to make a battery. Batteries need what for their cell potentials? Positives. And I'm getting a negative, which means it's non-spontaneous, which means I'm wrong. So what do? Start over's a little bit overzealous, but I totally understand where you're going with that. It just means I flipped the wrong equation. Okay? So what does that mean I'm going to have to do?
Flip everything.
I'm going to have to flip everything. Okay? So the aluminum is going to be the equation I'm going to flip to aluminum plus 3, plus my 3 electrons. So instead of it being a negative, I'm going to multiply by a negative now because I flipped that one, and that will become positive. What happens with the lead? I'm going to flip that back to where it was, plus my 2 electrons to lead. Okay, because I flipped it again, I can make that a negative, or simplify, just drop that down as a negative. And now what happens? I get a cell potential that is positive 1.53. Okay? If I did this right, we have a couple checks that we could run within this. Okay? What should happen to the electrons? If I look at an overall equation, should I see electrons? No, so the electrons should cancel. So that means I should see electrons on the reactant side, do I? Yes. And electrons on the product side, do I? Yes. So that means I've at least flip-flopped my equations appropriately. I now have a decent cell potential. But what do I notice if I look at those electrons? They're not the same, which means they don't cancel. What would I have to do to ensure that the electrons canceled? I don't know that I would use the word balance. It's not wrong. I'm not sure I like that word. Okay, how would you balance? So I just add one more electron? No, I can't just add electrons into the system. How do I get more electrons? I run that reaction multiple times. Well, how many times do I want to run it? I want to run it until the numbers, our electrons, cancel out. So how do I figure that out? Well, I could just start multiplying random numbers, or I could look at the 2 electron counts and say, what's the lowest common multiple? Math people, did I phrase that right? Okay. I always question that. So what's the lowest common multiple between 2 and 3? 6. What? Do they have to come out to the same number? Yes. Because why?
No, I mean, does what you multiply the top by have to be the same as what you multiply the bottom?
No.
Okay.
Nope. Okay. What we have to ensure is the electrons always cancel, period. Okay. So what do I have to multiply the top equation by to get 6 electrons? 3. Okay, so 3 times 2, there's a 3. There's a 3. What do I multiply the bottom one by? 2. 2 times 3. 2 times 3 and 3 times 2 conveniently are the same thing, so those would cancel out. And my overall equation becomes 3 lead plus 2 aluminum. Takes me to 3 sorry, I should say lead ion, to 3 lead plus 2 aluminum ion. Now I have a proper overall equation for this system. Ooh, but if I multiplied by numbers through the equation, should I be multiplying those numbers into my cell potentials? No. And I wish I had a better answer for why. I don't remember why. Sorry. It's what happens when you teach the class once in 15 years. Okay? So you don't multiply your cell potentials. You leave those alone. Okay? Questions? Okay. So, voltage is affected by changing conditions. So, temperature will affect our voltage. Why would temperature affect our voltage? What does temperature affect? I accept that. Energy. What's our symbol for energy? You started it, not me. E is our cell potential. What's our symbol for energy? Delta G. Okay? Does delta G have a temperature dependence? Yeah? So delta G, and I should be able to write an expression now where I see how it has a temperature dependence. What expression shows a temperature dependence? I can think of 2. You all theoretically have been doing more work on this than me, so you should know it better. What's that? Negative RT ln of K. Okay, so if we change the temperature, what happens? Delta G will change. Okay, we can see that in this expression. Okay, that's actually the useful one that I wanted to look at, but we also have potentially delta G equals delta H minus T delta S. Does a change in temperature affect our delta G? Yeah. Okay. So, cool. Temperature affects delta G. This is saying cell potential. You just told me delta G. Why does cell potential have a temperature dependence? You just told me delta G has a temperature dependence. They're equatable. You mean? I already forgot the equation. Delta G. I think it's still delta G.
Yeah.
Delta G equals NF cell potential, which means we could go through and say both of these equations are relatable to each other, and I can get RT ln of K. Okay. Why is that going to become useful? This shows me, if I rearrange and solve for our cell potential, that the cell potential is going to be dependent on temperature. Cool, I can see that temperature dependence. Okay. I can also see concentration in this. How do I see concentration in this? Does concentration show up in that equation? What's K? What's K? The concentration of our products. It says products, trust me. And again, reactants. So yeah, if we start changing the concentration, that will also affect my cell potential. Okay? So all of these things are tied to each other. That's the beauty behind it. This now also says pH. Well, dang. How could pH possibly affect our cell potentials? What is pH? H plus is the negative log of concentration, pH, I flipped it. pH is equal to the negative log of our H3O plus. Does H3O plus concentration show up in our K expression? It can. And if it shows up in the K expression, is that going to have an effect on our cell potential? Yes. So what we're seeing is how all of those independent units can all stack and kind of interact into this overall system. Okay? Someone else went through and did this and noticed and called this the Nernst equation. Okay? So what Nernst went through and did is he recognized our standard cell potentials. How do we know that one's the standard? Yeah, the little zero up there is our standard. Okay, the standard cell potential made certain assumptions. What was one of the assumptions?
25 degrees.
25 degrees Celsius. It's awesome. I knew you were going to say that's not the assumption I wanted. What was one of the other assumptions? Yeah, that's the one I was fishing for. Okay, the concentrations of all of our species were 1 molar. Okay, why has that become important? 1 molar or 1 ATM. Typically when we're thinking about batteries, we're thinking about things that are aqueous. So that's why I've immediately launched into molar. Okay. Why has that become important? Well, we could look at our equation, and instead of being at equilibrium or off equilibrium, we could look at Q. What was Q? What do we solve for Q? Products over reactants. So I could create a system where I can manipulate the concentrations of my reactants and products to alter the standard cell potential. Okay, why not K?
Is it equilibrium?
Sure, K is at equilibrium. Why does that matter? Why do I not look at K?
Wouldn't it just be always the same as the standard E?
Okay, if I go through and sub in K, what does it mean to be at K? It's not 1. K is not 1. This gesture with your hands was a good gesture. The rate of the forward equals the rate of the reverse, which means what's the net electric flow?
0.
0, which means if we were at K, what happens to our non-standard cell potential? It's 0. Okay, we would get no flow of electrons if we were at equilibrium. Our voltaic cells, what we're trying to generate is be off of equilibrium, because what the reaction is trying to do is obtain equilibrium. That reaction trying to become in equilibrium is what's generating the electric voltage. So we tend to ignore K expressions or at equilibrium systems here because it doesn't do what we want it to do. We're trying to generate power. We're not going to get that power if we look at equilibrium. Okay? This can also be kind of fun and useful because if we go back to our salt bridge system here, we could pick 2 identical things. We could go through and make this copper and make this copper ion. Would I expect to see the electrons flow? The reduction potential forward will be equal to the oxidation potential, but opposite the other direction, which means our standard cell potential is 0. So that's not useful. We would never do that. Okay? But if I manipulate the concentrations of those ions and I alter them in the correct fashion, which I don't know off the top of my head, okay, what will end up happening is I will see those ions start to move. So let's say that they were really high concentration here and low concentration here. What's going to happen? What's going to pass through that salt bridge? These copper ions are going to move that direction to dilute it. If you're ever trapped out in the ocean and you're really thirsty, what do you not do? Drink the salt water. Why not? The water in your body is naturally going to flow to dilute the salt. That's going to take all the water out of your cells and put it into your waste stream to dilute the salt concentration. You're doing the exact same thing here. Our ions are naturally going to flow from a high concentration to a low concentration. If the ions start to move that direction, what's going to start to happen to the charge? It's going to be imbalanced. How do we fix that imbalance? electrons. Right? And again, I'm probably drawing the arrows wrong. You shuttle electrons through a wire that connects that loop. Right? Why is that useful to me? Well, if I'm on a desert island and I don't have a battery to charge things up, what could I go through and do? I can start to distill water. Oh, it's not that hard to distill water, but I can distill water. And if I come up with a couple different concentration gradients, I can take salt water, high concentration salt, and allow the ions to flow through a salt bridge all the way to the very dilute solution. If I now have enough wire to connect them all back around, that wire will now push electric current. And I now have a primitive battery. Right? That's just based off of taking advantage of not electric flow, but our ion flow, which is ultimately what our Nernst equation is doing. Right? That's the whole point of Q, products over reactants. Okay? That's kind of a neat system to go ahead and leverage. Hopefully you're never trapped on a desert island, but now you'll know how to make a battery. You'll probably still die because you don't have any food, but at least you have electricity. Okay? So calculate your cell potential when copper ion is 1.5 and your zinc ion is 0.002 molar at 298 Kelvin. Okay? What happens to the cell potential is our reactants decrease and products increase over time. If we think back to our Nernst equation, it says products over reactants. Does it say the copper plus 2 ion is a reactant or a product? Right? If we read the question actually doesn't tell us that information. How would we know whether it was a reactant or a product? Read the equation. So the equation is going to set you up with slightly more context to allow you to know where your reactant and product are. So you should now be able to go through and navigate and set this up. If you've got questions, you can raise your hand. I'll come to you. And I'll also try and write up the Nernst equation here so you've got access to it. So we can effectively just start plugging things in. Okay, so our cell potential, our standard cell potential was given to us. That's our 1.104 volts minus R. Our R will be our gas constant, 8.314, 298. So we can drop in our 298. Okay, I've got a suspicious blank space here. What was that suspicious blank space for? The number of electrons transferred. How do I know the number of electrons transferred? Okay, so again, since this is the first time someone mentioned it, we could go through and look at our charges. What's happening is we're going from copper plus 2 to copper 0. Okay, so you've immediately reflexed that that's going to be 2 electrons. Whether it's gain or loss, we don't technically need to know. We just need to know how many electrons were transferred. Okay? We might need to be a little bit more careful in a system where it's not an equal transfer of electrons. In that case, what I would recommend you do is pull out and look at your half reactions to figure out exactly what's happening with your half reactions to ensure that you actually have the proper transfer of electrons. Make sense? So in this case, we could put in the 2. We've got our Faraday's constant, and then we go through and do our products over reactants. How do we know the 0.02 belongs in the numerator? The 0.02 belongs to our zinc ion, and because we know Q is products over reactants, our zinc ion shows up on the right-hand side of the arrow, which means that's our product. We need to put that in at the top, and we get our 1.18. Okay. Within the work that's shown here, there are some suspicious blank spaces. Why would there be suspicious blank spaces? Units. Why would that become important? How many points do you want to lose on every frickin' quiz for not writing your units? It's up to you to decide. Okay? But it's in the question every single time, and every single time people are like, why did I lose points? You didn't write the units down. Okay? If it asks for them, you need to include them. What are the units on our 8.314? Joules per mole. What's our units on our 298?
It's joules per mole Kelvin, right?
Sorry.
Yeah.
Kelvin. What are the units on our 2?
Moles electrons.
Okay. The one case where you don't have to worry about units is actually dealing with our Q. Okay, you'll note that when we talked about K and Qs, we never really dealt with units. Why not? You could say, well, it's moles over moles, sort of. We could say molarity over molarity is a little bit better. Even then, what happens when it was a more complex expression and you had products squared over reactants? Okay, right? Because you have to bring in that coefficient. Right? There, your units aren't canceling. So what the heck happened? What happened is the reality of the system. What we're looking at when we talk about Q's and K's being concentrations is only a first approximation. The reality of the situation is that it is far more complex, and when you go into those far more complexities, what you actually look at is the activity of each individual reagent. The activity is factored in based off of concentration, and ultimately the activities will all cancel out. Since we don't want to deal with the complex unit systems of activities, what do? The same thing you've all been doing on the quizzes. Ignoring the units. Okay? So we ignore the units when dealing with K and Q, ultimately because we aren't solving for them appropriately. Okay? That's the easiest answer for that. We would then go through, get our 1.18, which would be in units of volts. Is this a positive or a negative? Cool, it's a positive value, which means is this a spontaneous reaction? Yes. Okay. Now the last question. What happens to the cell as the reactants decrease and the products increase over time? How do we figure that out? Right? One option is just testing. If our products increase, instead of it being 0.02, let's make it 0.1. Okay? And you're like, well, but how do I account for how the products or the reactants will now change and correlation behind that? You could go through and quantify that in a more accurate fashion, or you would just go through and say, if the products increase, our reactants decrease. Instead of looking at 1.5, I'll just make it 1, just for giggles. I could now go through and run the calculation and see what I get. Okay? And when I run it, what do I discover? Say again? It decreases. Does it make sense for it to decrease? Yes. What's happening as our products increase and our reactants decrease in this case? They're approaching K. And once we've obtained equilibrium, our battery is dead. And so the cell potential will approach 0. Okay, so that's what's happening within those individual systems. That was probably bad timing. Do you have questions? Cool. Why is that important? Because this stresses back to how batteries work. Our electrons are constantly flowing, or not constantly. When under load, our electrons will flow from our anode to our cathode in a spontaneous reaction. Those electrons moving are what our electricity is. We've got salt bridges within it that'll act as an electrolyte. Okay? And then eventually what happens is all the reactants are converted across to products. As soon as those reactants are converted across to products, we no longer have a spontaneous reaction and our cell potential becomes 0. Okay? What I wanted to look at was this. Okay? And we'll go ahead. So how important is a salt bridge? So to answer that question, what I would do is go back to our pretty picture. What happens if I delete the salt bridge? Okay. For the electrons to flow out of here, this side starts to become positive because it's losing electrons. This side starts to gain electrons, so it's starting to become negative. Okay? It's going to start creating an imbalance of charge. As soon as it creates an imbalance of charge, if there's enough electrons on the right-hand side, can I feed more electrons into it? No. So what happens? The electrons don't move. It stops that location. Right? The whole point of the salt bridge is that I prevent the buildup of charge. So while this electric flow starts to build a negative over here, what do I have to do? I'm going to start shuttling negative ions the other direction, so that those negative ions can counterbalance and neutralize that buildup of charge. So how important is that salt bridge? It's what actually allows for the completed circuit for your electrons. Without that salt bridge, you don't have a battery. You just have a bunch of chemicals in a couple pots. Okay. So what this is looking at is how your cell decreases over time. So what you'll end up seeing is your batteries start to lose power. So if we're looking at a battery that initially had 1.5 volts, okay, it's going to start to generate less and less power until eventually it has no power. Right? Has anybody actually taken a multimeter to a dead battery? Right? And what you'll find is how much volts. How many volts do you think you would see coming out of a dead battery? You would assume 0. Guess what it is? It's about 1.3. If your battery was supposed to produce 1.5 volts, your dead battery will produce 1.3 volts. What the hell? It's got an extra 1.3 volts in it. Why can't I use it? It's not generating enough electric flow for the load of whatever you were trying to design it for. Right? So our battery's lifetime is really only in this threshold. That's what this green line is referencing, is the threshold before the battery is dead to us. It's still living, but we don't care about it. I can make lots of bad jokes. Let's not do that. Right? But that threshold is where our battery is no longer useful. Okay. So, why aren't you going back? Oh, it did go back. Weird. So if we go through and look at an alkaline battery that contains electrodes made of zinc and manganese oxide, write the overall spontaneous reduction reaction that occurs, calculate the value of your cell potential, and determine the anode and the cathode. You guys said you wanted practice. You want more practice? Yeah? Do it. Walls talk to me more than this class does. And I would know. I've recorded plenty of lectures against walls. Okay, so in trying to go through and process how we navigate this question, okay, I've added little kind of tidbits within it that I would personally add to my equation. First and foremost, I would make sure I can see my reaction arrows, so I would highlight those. I also underlined the electrons so that I know where the electrons are relative to my arrow. This helps because it's now showing that I'm looking at reduction potentials for me personally. That means the cell potentials that I'm given are all reduction potentials as well. Okay. Now I'd move through into the question. It says, write the overall spontaneous. I want to stop and say, okay, spontaneous. What does spontaneous mean? A spontaneous reaction as far as voltages or as far as our cell potentials is going to go is that the E cell is positive. I don't know why I said 0. Is greater than 0. So I need a positive value. Okay, not greater than or equal to, but greater than 0. So I can now go through and look at the cell potential numbers I've got. Okay? If I look at putting those together, I'm going to have to do something with them, because if I just straight add them, I'm going to get a negative number. I need it to be positive. Okay? If I flip the top one, that's a negative number. A negative number and a negative number is going to be more negative. Okay? It's not a negative times a negative. Okay? So that doesn't work. So I'm going to have to flip the bottom equation. So once I've established that I need to flip this equation, I now am going to go into writing this out. So if I flip that equation, I've got my zinc plus my 2 hydroxide is now going to go to zinc oxide plus 2 H2O plus my 2 electrons. Okay, the electrons are on the product side of the equation, which means that was my loss of electrons. This was my oxidation. The other equation I'm going to leave alone. Again, I would pick my arrow as my focal point behind it. For whatever reason, I would start writing to the right of the arrow. It's just what happened. And then I would double back to deal with the other side. 2 electrons, my H2O, and my 2 MnO2. Okay? The electrons are on my reactant side, which means I gained electrons. That would be my reduction. What's going to happen is I'm now going to go through and add those 2 equations up. to get my overall equation. So everything on the right-hand side needs to become a reactant. Oh, I'm going to commit. 2 electrons, zinc oxide plus our H2O plus our 2 electrons plus the Mn2O3 plus 2 hydroxide. Okay. Once I've got my overall equation, I then want to process, is there anything I can eliminate? Does anything show up the same on both sides of the equation? Yeah, the electrons do, which means I could drop those out. Okay. I will also note that the hydroxide shows up the same on both sides of the equation, which means I can drop those out. My overall expression, I can't believe I suckered myself into this. Whoops. And I put a 2 H2O. So then the water perfectly cancels out as well. So I'm going to get my zinc plus my 2 MnO2 plus my zinc oxide plus my Mn2O3. Okay, that now is my overall equation. If, say, this was on a quiz and all I wrote was that bottom equation and I did this, I'd be wrong, right? I wrote the wrong equation. If I wrote none of the other work, have I provided any evidence that that was just a typo? Nope. Because there's no evidence that that's a typo, what happens? I lose lots of points. If I provide all of this work that I've written out above, I can now show evidence that that was just a simple mismatch in how I was writing out the equation, and I just forgot to put in those numbers. That's a please pity me, I just screwed up a small mistake. There's evidence that that was totally unintentional. Give me my points, please. Okay? That's why we write our work, to provide evidence that we understand what's going on within the system. What happens with our cell potentials? We flipped the blue one, right? If we flipped the blue one, I lost which one it was, the bottom one. It was a negative 1.28 volts, but I flipped it, so that's going to become positive. The other one was just a 0.15 volts. All I got to do is add those two numbers up, and I would get my cell potential for the reaction of being 1.43 volts. Yes, sir. I circled the 2 MnO2 to call attention to the typo that I had unintentionally made, to call attention to the fact that we should show all this work to ensure that we can get maximum points. It's not the same thing as answering that yet. Okay? So the next part of the question is which is the anode and which is the cathode. And so what you would note is, again, what did I do is as soon as I saw anode, I immediately said oxidation, and I also tied in loss of electrons. Those are notes for me internally. Again, I would argue that's work. And so that if I just left it as this, do I have enough evidence written down that I know the reaction that's happening at the anode? Yeah, I may not have explicitly stated it, but I have enough context in the random notes that I've got that I would hope whoever was grading would give me the benefit of the doubt. Right? But for the sake of the question, we should be a lot more explicit in defining what's happening at those things. Make sense?
So could we just say like the bottom reaction is the anode and the top reaction is the cathode?
The bottom reaction is the anode.
Oh, I was referring to like a...
Yeah, that becomes the problem. So you got to make sure that you're real explicit with what thing you're saying. So if you were going to write up at the top one was the anode and the bottom one was the cathode from the top, I just flipped it from what you said. Okay, but you have to make sure you're tying it to the equation appropriately. As long as you do that, that's fine. Yeah, Thomas?
You don't have to like label anything with your final equation that you get.
I mean, boxing it wouldn't be a bad idea. That's really just trying to be kind to the grader. Do you have time on the exam to be kind? Yeah? Then be kind. If you don't have time, don't worry about being kind. Worry about getting right.
But it isn't time.
You could go through and start saying what thing specifically was the anode, okay, I'm the one grading it, I'd be fine with that. You've identified enough of the reaction that I'm happy with it.
Oh, so you don't have to write the states of matter for each of them?
How much time do you get? That's what I would argue, unfortunately. So, should you have the states of matter? Yeah, I think you should. You can tell how much I like showing states of matter, particularly for an equation this long. That trying to drop in that states of matter, that would be let's make sure I can't get nitpicked points on this. For me personally, since I'm the one grading it, I would let it drop. Unless what? Not that it matters. The question asks for it. Okay? So when I go through and write down keys, I'm looking at the question, and if the question specifically asks for it, I'm specifically looking for it. Okay, in that statement. So could it ask for that? I sincerely hope not. Okay, we're almost there, but I do have just some kind of factual slides I think would be useful to get through. Do want to point out this Friday, I am not here, so don't try and find me in office hours this Friday because it's not going to happen. So redox reactions will also play an important role in biological systems, which is getting at what you were talking about, Jared, about what's happening with your cell potentials. Because this context will actually, some of the problems that we're going to talk through, not today, are tied back to this concept. So if we look at important biological reactions, they will go through redox reactions. And if they're going to go through redox reactions, they're going to have reduction potentials. And if they have reduction potentials, what should we be asked to solve for? Cell potentials. Okay? Which is then going to push and change things up a little bit, because on that last question, I had one of your classmates say, I'm just going to flip whatever one's the most negative. We have to be real careful with that, because that only works when making a battery, because we want the battery to have a positive cell potential. This is not a battery. This is what's actually happening. So we're in a system of what's actually happening. You need to make sure that the reaction you're presenting matches what is actually being told to happen. Okay? So we'll pick up with this question at the start of, what is today, Tuesday? At the start of Thursday. And then we'll talk through a bunch of other things, I guess.